Next, another one is in the molecular spectroscopy, the electronic spectroscopy. In electronic spectroscopy, in the last class I already explained, in the continuation of that. So, if it is a number of atomic orbitals mixing takes place, equal number of molecular orbitals are generated by the combination of the linear combination of atomic orbital method. Linear combination of the atomic orbital method. If atomic orbitals of the different atoms, if atomic orbitals of the same atom mixing takes place, that it may be going to be lead to the hybridization. If it is different atoms, so atomic orbitals mixing takes place in the linear combination of the atomic orbital method, molecular orbitals are generated. In the linear combination of atomic orbital method, linear equal number of molecular orbitals. If n number of atomic orbitals mixing takes place, n number of molecular orbitals are generated. In that method, if n number of atomic orbitals, if it is mixing takes place in that linear combination of atomic orbital method, if that method is maybe addition method, if it is follows addition, or subtraction method if it is follows. So addition means addition of the molecular orbitals adding, and subtraction if it is different. So based on that, addition and subtraction methods if it is there, if it is follows, or the molecular orbitals, the generally linear combination of atomic orbital method means if it is molecular orbitals are generated. Equal number of molecular orbitals when generated equal to the atomic orbitals. Now, in this linear combination of atomic orbital method, if follows particularly addition method, or molecular orbitals which are generated from the addition method, that molecular orbitals which is called as the bonding molecular orbitals. That molecular orbitals which is called as the bonding molecular orbitals. And if it is subtraction method, if the molecular orbitals which are generated from the atomic orbitals, that molecular orbitals which is called as anti-bonding molecular orbitals. Anti-bonding molecular orbital and bonding molecular orbital. ABMO means anti-bonding molecular orbital. BMO means bonding molecular orbitals. And if it is n value, if it is even, n is equal to even, which is not at all important. So here it is n by 2 number of bonding molecular orbitals which are generated, n by 2 number of anti-bonding molecular orbitals also which are generated. Bonding and anti-bonding molecular orbitals. Now, whatever the molecular orbitals which are not participated in the bonding, the molecular orbitals which are not participated in the bonding, which are not participated in the bonding means lone pair of electrons, pairing of electrons. So that electrons which is there, that one is considered as the non-bonding molecular orbitals. Non-bonding molecular orbitals. Bonding, non-bonding and anti-bonding molecular orbitals which are there. The generated molecular orbitals are bonding molecular orbitals, anti-bonding molecular orbitals, another one is non-bonding molecular orbitals. Based on the energy criteria, energy of bonding molecular orbital which is less compared to the energy of non-bonding molecular orbital compared to the energy of the anti-bonding molecular orbital. Or which one energy is more? Anti-bonding and orbital energy is more compared to the non-bonding compared to the bonding. Right? So based on this one is there. Now here it is, why this concept we are using here in this UV visible spectroscopy for the electronic transitions case, that may be important point of it. Electronic transitions point of view, we are using this concept. And again, before this, if it is sigma orbital, suppose if it is s orbital, if it is there, having one electron like this, and if it is s orbital, if it is mixing takes place, these are two atomic orbitals. This is one atomic orbital, this is one atomic orbital. If two atomic orbitals mixing takes place, how many number of molecular orbitals are generated? Two molecular orbitals which is generated. When S and S it may be going to be takes place, which bond formation takes place? Sigma bond formation takes place. Sigma, generally sigma bond formation takes place, sigma. So in that sigma bond formation takes place, sigma bonding molecular orbitals are generated, sigma anti-bonding molecular orbitals are generated. Bonding as well as anti-bonding molecular orbitals. So, 2 atomic orbitals mixing takes place, 2 molecular orbitals generated. The 2 molecular orbitals are generated. One is which one? Sigma bonding molecular orbital. So, that's what here in this case, suppose like this plus and plus, if it is like we have to consider, suppose sigma molecular orbital, and if it is plus and minus, if it is there like this, sigma star antibonding molecular orbital will be generated. Sigma star antibonding molecular orbital, which generally we can use in the case of the p atomic orbitals case. I can explain this entire concept by considering this p atomic orbital. Suppose if it is a p atomic orbital, another one p atomic orbital will be considered minus plus plus minus. Right, both these 2 p atomic orbitals, if it is mixing takes place in the linear combination of the atomic orbital method, in the linear combination of the atomic orbital method, this is p and this is p orbital. If these 2 will be addition method, if it is there, if it is using the addition method, if it is using the addition method, suppose I can mention like this, suppose minus, and this 2 addition takes place, right? So here it is plus and minus if it is there, plus minus if it is there. So here it is which bond formation takes place? Sigma bond formation takes place. So this one is considered as sigma bonding molecular orbital. Sigma bonding molecular orbital. Another one molecular orbital which is generated from the subtraction method. From the subtraction method, which one is generated from the subtraction method? So here it is. So here it is minus plus, and here it is minus plus. So which is opposite direction, right? And there is a between these 2, there is a node or nodal point which will be generated. Minus and plus, which cannot be combined like this, right? So one is empty, another one is fulfilled like this. So between these 2, there is a node or nodal point which is generated like this, node or nodal point which is generated, and this is, there is no bonding here between these 2, that it may be considered as which one? Anti-bonding, that it may be sigma star anti-bonding molecular orbital. So one is sigma is generated, another one is sigma star anti-bonding molecular orbital which is generated. Here it is, there is no non-bonding in this particular case. Next, if it is these 2 p atomic orbitals plus minus if it is there, these 2 p atomic orbitals mixing takes place, 2 molecular orbitals are which are generated. So these 2, due to the partial overlapping, if it is there in the LCAO method, these 2 if it is in the partial overlapping takes place. Partial overlap. Generally, partial overlap, direct overlapping takes place, sigma bond formation. Partial overlapping takes place, which bond formation takes place? Pi bond formation takes place. So, due to that, the partial overlapping, if it is addition method follows, if it is follows the addition method, which one will be generated? So, this one, these 2 overlapping takes place, these 2 overlapping takes place. That means plus plus and minus minus. So which bond formation takes place? Pi bonding molecular orbital. Pi bonding molecular orbital. Pi bonding molecular orbital. Next, if it is subtraction method, if it is follows, subtraction method if it is follows, what will be happen if it is subtraction method if it is there? So if it is plus minus is there, and here in this case minus and plus is there. Between these 2 there is a node or nodal point which is generated. Between these 2 there is a node or nodal point which is generated. This it may be called as pi star anti-bonding molecular orbital. Pi star anti-bonding molecular orbital. Now in the sigma, sigma star and pi star case, sigma, sigma star and pi star case, so I can give one conclusion here in this case. If molecular orbitals having whatever the molecular orbitals, sigma, sigma star, pi and pi star molecular orbitals, the molecular orbitals having the CI symmetry, it may be there, center of inversion if it is there, CI symmetry or center of inversion is there, center of inversion if it is there. When molecular orbitals having center of symmetry or center of inversion is there, that having gerade and symmetric, that having gerade and symmetric in nature. That gerade can be shown like that small g. Gerade can be shown that small g. So here this molecular orbitals having, there is no center of inversion, CI symmetry is not there, that it may be called as ungerade. This is a German words, ungerade. So this it may be shown like this U. Ungerade it may be the U, and that it may be considered as like antisymmetric in nature. Gerade, ungerade, because based on the gerade symmetry selection rules in the electronic transitions, in the selection rules, based on the symmetry criteria also, gerade and ungerade also it may be played a key role, right? So that's what gerade and ungerade it may be also there. Now here it is, in the case of gerade and ungerade which is there, pi star if molecular orbitals are there. Now this concept will be applied to this pi star, sigma and sigma star case. Now the molecular orbitals having CI symmetry, that it will be considered as gerade. See, listen. In the sigma orbital case, plus and plus it may be there, so it may be considered as gerade, right? Sigma orbitals having gerade, center of inversion which is there, CI is present. And here it is minus and plus will be there, there is no CI. CI is not there. So CI is not there means this pi star molecular orbitals, which one? Ungerade. Sigma star molecular orbitals are ungerade. Now coming to the pi case, so here it is plus minus and plus which is not there. Plus minus different opposite, and minus and plus which is going to be opposite. So that's what the pi molecular orbitals which is going to be ungerade. CI is not there. CI is not there. This is going to be pi bonding molecular orbitals are going to be ungerade. And here in this case, pi star case, plus plus and minus minus, when it is CI which is present. So CI is present, so pi star molecular orbitals will be gerade. Pi star molecular orbitals will be gerade. So based on this gerade and ungerade concept, what is gerade and another one is ungerade concept. The electronic transitions, one of the selection rule which may be generated for the electronic transitions purpose, see, listen. The molecular orbitals which is going to be, which one? Sigma molecular orbital, sigma bonding and pi bonding, pi star and sigma star, right? And where CI symmetry element is present or not, center of inversion, and based on that symmetry which is going to be gerade or ungerade, See, listen. Sigma orbitals having center of inversion is there or not? No center of inversion. If center of inversion is not there, center of inversion is not present, that it may, center of inversion is present, that it may be considered as symmetric. Yes. Right? When it is considered as gerade G. Right? And coming to the case of sigma star, suppose, which is center of inversion is not there. So it may be antisymmetric or sometimes symmetric also. Antisymmetric, A it may be considered, right? A with respect to the CA. So which is going to be ungerade or gerade? Ungerade. So that it may be U. And another one which will be what? Pi bonding molecular orbital. So in case of pi also, there is no center of inversion, antisymmetric which is there, and which is also going to be ungerade, U. And pi star which is going to be pi star, so here it is symmetric center of inversion which is present. So based on this, pi star molecular orbital which will be gyrated. I mentioned that pi star will be gyrated, right? So this one concept which is gyrated, ungyrated, and whatever that it may be there, symmetric or anti-symmetric, like this. Which orbital, you have an idea about that, which orbital which is going to be gyrated and ungyrated, like that. Based on that only the further electronic transitions which are possible in the molecule. Symmetry rule, gyrated to ungyrated is possible or not, I can explain. Gyrated to ungyrated is possible or not, I can explain the transitions. Or all case it may be possible or not, based on selection rule will be further governs the electronic transitions, right? Next in the case, another one, this is according to the symmetric criteria, further we can explain this based on this. Another one, multiplicity criteria is also there, further explanation of the symmetric selection rule based on the multiplicity also which will be there. Based on the multiplicity also, another one criteria is there. What criteria is there according to the multiplicity? I can explain according to the multiplicity. Before multiplicity, what is an electronic transition generally? What is an electronic transition? So we are using for all these for the electronic transitions purpose, because in the examination point of view, electronic transition is also based on that examination, electronic transitions questions are there. So what is an electronic transition? This total electronic spectroscopy based on the electronic transitions only. Electronic spectroscopy or UV-visible spectroscopy. UV-visible spectroscopy, electronic spectroscopy, electronic transitions. What is an electronic transition? Electronic transition. The first one is which one is considered as an electronic transition? So when electron jumps from promotion of the electron, this is a ground state level. This is a ground state level. Ground state. This is what? Excited state. Excited state. Or this is considered as HOMO level. This is considered as LUMO level. This is considered as, suppose, HOMO, highest occupied electron molecule, highest occupied energy with electron, molecular orbital. Lowest unoccupied, right? Lowest unoccupied molecular orbital. That means without electron, lowest energy unoccupied molecular orbital, highest energy occupied molecular orbital. HOMO and LUMO will be there, right? If so many of the bonding states will be there, you may consider like that HOMO, right? Now based on that HOMO, LUMO, or whatever it may be, excited state and ground states, if shifting of the electron, these two electrons which is there, shifting of the electron or promotion of the electron, shifting or promotion. Shifting or promotion of electron. Promotion of electron from which level? From ground state to the excited state, or from one HOMO level to the LUMO level, or one molecular orbital level to the another molecular orbital. Shifting or promotion of the electron from one level to one molecular orbital to another molecular orbital, or that molecular orbital it may be HOMO to LUMO. That molecular orbital it may be HOMO to LUMO. HOMO to LUMO, shifting or promotion of the electron from one molecular orbital to another molecular orbital. That is HOMO to LUMO, or ground state to the excited state which will be takes place. That will be considered as which one? Electronic transition. That is called as which one? Electronic transition. So if it is going to be takes place, what will be happen? One electron here in this case and another one electron here in this case, right? That it may be considered as electronic transition. Now, shifting of the electron or promotion of the electron, you know that one level to another level which is considered, that it may be considered as the electronic transition. In that electronic transition, so this, it may be takes place from HOMO to LUMO, LUMO to HOMO, like that. So we know that in the earlier one, based on the energy criteria, one it may be considered as the bonding molecular orbital, another one it may be considered as the anti-bonding molecular orbital, another one we have to consider as the non-bonding molecular orbital. Based on the energy criteria also, this direction it may be there. Now, bonding molecular orbital having the pair of electron which is there, and non-bonding also lone pair of electrons if it is there, that it may be going to be non-bonding, right? Lone pair of electrons if it is, which is not participated in the bonding, lone pair of electrons. Pair of electrons if it is there. And the anti-bonding molecular orbital generally which is an empty, which is a non-bonding, so which is anti-bonding, right? Node will be generated, that is going to be an empty. So that generally which is considered as the LUMO level, these two considered as the HOMO levels. HOMO levels depending upon that, whatever that which is going to be HOMO depending on the particular molecule, based on that energies, right? Now, the electronic transitions which are possible, because which levels are there in generally bonding level, non-bonding, anti-bonding. These three molecular orbitals are only there. So from which level to which level which is generally possible electronic transitions are the bonding molecular orbital to anti-bonding molecular orbital, which is promotion or shifting of the electron takes place from one level to another level. That level will be bonding molecular orbital to anti-bonding molecular orbital, bonding molecular orbital to anti-bonding molecular orbital. Electronic transitions are possible. The second one, which is going to be non-bonding molecular, which is also having electrons which is there, non-bonding molecular orbital to which orbital? Anti-bonding molecular orbital. Non-bonding molecular orbitals to anti-bonding molecular orbitals, electronic transitions are possible. But the electronic transitions are not possible from anti-bonding to the non-bonding, anti-bonding to the bonding, which is not possible. Reverse manner which is not possible. So that means sigma star to sigma is not possible. Sigma to sigma star it may be possible. Pi star to pi it is not possible. Pi to pi star it may be possible. The direction it may be bonding to anti-bonding or non-bonding to anti-bonding electronic transitions are possible. This is one of the criteria. So later it may be, even though in bonding to anti-bonding case, suppose which is sigma is the bonding, pi star is the anti-bonding, but sigma to pi star which is not possible. Based on the which criteria, symmetry criteria, I can explain later, JRED and JRED concept point of view. Some selection rules will be there. And non-bonding to anti-bonding is also, it may be possible, right? So, but it may be N2 pi star case and N2 sigma star case which is possible, but here it is pi star to N which is not possible, right? So, some selection rules will be there. So, further I can explain bonding to anti-bonding or non-bonding to anti-bonding molecular orbital, or in generally, in other words, HOMO to LUMO also it may be possible. HOMO to LUMOs also it may be possible, generalized case. Now, this is one of the electronic transitions possible is what? Electronic transitions are possible is what? Before going to be selection rule, in the electronic transitions case, after selection rules only we have seen some of the examples, right? Which one is possible, which one is not possible. Before selection rule, another one term I can explain in the electronic transitions case, multiplicity J, which can be shown like that, J. So multiplicity J is equal, which is going to be modulus 2s plus 1. Modulus 2s plus 1. So, where S it may be the sum of the spins of the individual electrons. Sum of the spins of the individual electron. Sum of the spins of the individual electron. So, it may be the spin angular momentum quantum number that will be calculated. How to calculate sum of the spins of the individual electrons? That will gives the resulting spin quantum number value. This is resulting spin quantum number value which can be obtained sum of the spins of the individual electrons. Sum of the spins of the individual electrons. So based on that, if spin having, right, so it may be 1 or 2, it may be there, or 0 value it may be there. So how it may be there? Most of the case we know that. So any molecule is in the ground state level, any molecule which is in the ground state, which is present in the ground state level, having pairing of electrons are there. Pairing of electrons are there. The electrons are paired in the ground state because it may be stable, having low energetic, low energy, having stable. So that's what which is having pairing takes place. When it is having pairing takes place, when it is having pairing, so which is going to be plus half spin and which is going to be minus half spin. So the total spin is what? S is equal single S1 plus S2. Only this is S1, suppose this is S2. So S1 is plus half, S2 is what? Minus half, which is going to be cancellation takes place, spin will be 0. When S will be 0, what will happen? J will be modulus 2S plus 1. The modulus means whatever the value. S value, if it is minus 1, suppose it may be obtained, you can take that it may be plus 1. Modulus meaning, right? So that modulus means plus. So 2 into S value is how much? 0. 0 plus 1. So that means what? 1. Now here it is, based on that J value, if it is 1 which is obtained, we can say that which one state that is. So J is equal to modulus 2S plus 1. If J is equal to 1 is obtained, J is equal to 1 is obtained, that state will be considered as the singlet state. That state will be considered as the singlet state, that is having capital S like that, singlet state. If J value which is obtained as 3, J value which is 3, that one we can consider as the triplet state. That state we can consider as the triplet state, that is having T. That is having capital T. Now triplet state, how the triplet state will be obtained? We know that in the ground state, all the ground state levels are which level? Singlet state, and singlet ground state level. S naught means ground state singlet level. Right? So if it is promotion of the electron takes place from one level to another level, from another level, one level to another level, this ground state to the which state? This is excited state. Excited state. So the promotion of the electron takes place from ground state to the excited state, ground state to the excited state, with two choices will be possible here in this case. With two choices will be possible. What is the two choices? If retention of spin is there or inversion of the spin is there. Retention of the spin means if ground state having this electron which one spin? Minus half. In excited state also, if it is going to be minus half spin is maintained, that it may be converse, that it may be called as the inverse retention of the spin, same spin. If this minus half spin is going to be in the excited state, in the reverse direction it may be there, that it may be considered as opposition of the spin or inversion of the spin. So there is a two possibilities which is there, retention of spin and inversion of spin. So here it is, inversion of spin, it may be takes place, what it may be there. Inversion of spin, here it is retention of spin during the electronic transition from one level to the another level. So if it is retention of spin, if it is there, retention of spin, what will happen? If retention of spin is there, retention of spin is there, what will happen? Ground state having this one is there and excited state having retention of the spin like this. Right? If inversion of spin takes place, here which one is there? Plus half here in this case, and this minus of spin is going to be again reversed, plus half. Right? If inversion of spin is there, right? Spin is going to be minus half is going to be plus half in the excited state. So if inversion of spin takes place, if it is produced triplet state or singlet state, if retention of spin takes place, it is produced singlet state or triplet state. See, the retention of spin takes place, so the multiplicity point of view 2s plus 1, S is going to be which one? This is, here in this case, plus half, and here in this case, minus half. The total one will be what? 0. So J is equal 2 into 0 plus 1. So J is equal 1. So that it may be which one state again? Singlet state. If it is retention of spin takes place, which state will be? This is going to be excited state. Even though in excited state, retention of spin it may be takes place, that it may be produced which one state? Singlet state. But it is not ground state. Which one? Singlet excited state. Suppose you can consider as S1 state, we may imagine. That may be considered as the S1 state. Right? Singlet state, it may be generated. In the excited state also, it may be singlet. Now, if it is inversion of spin, if it is takes place, inversion of the spin takes place. During the electronic transitions, if it is spin, it is going to be inversion. In the ground level, it may be half, plus half. In the excited state, not minus half, is going to be spin inversion takes place. Plus half, it may be there. Spin flipping takes place, like that inversion takes place. So, if it is inversion of the spin takes place, this is what spin it may be going to be. This is, S is going to be plus half. Here it is also which one? Plus half. Here it is also plus half. So, total plus half means what? S is equal to 1. When S is equal to 1, what will be happen? J is equal to 2 into 1 plus 1. Then which one will be obtained? J is equal to 3. When J is equal to 3, that level which is considered as which one? Which level? Triplet level. J is equal to 3, that level will be considered as triplet level. So, like this it may be considered as T or T1 level. Suppose we may imagine T or T1 level. Even though comparison of the energies also takes place in the singlet S1 level, T1 level case, S1 level which is having somewhat higher energy compared to the T1 level according to the Hund's maximum multiplicity rule. According to the Hund's maximum multiplicity rule, right? Singlet levels having more energetic than the triplet state. Singlet level having more energetic than the triplet state. S1 is somewhat considered as higher energy than the T1. S2 is considered as the higher energy, considered as the T2 levels. So, suppose if it is S1, this is T1 based on the energy axis, right? If it is S2 is there, if it is having T2 is there. If it is going to be Sx is there, if it is having Tx like it may be there, right? Singlet, first excited singlet state, second excited singlet state, third excited singlet state. So like this electronic promotion of the electron takes place from the first excited state or second excited state or third excited state. Based on that S1, S2, Sx it may be generated. And T1, T2, Tx also it may be generated like this based on this, right? If it is shifting to the first excited state, T1. If it is the electron is going to be second excited state with retention of spin or inversion of spin, based on that S1, S2, T1, T2s will be generated. So T1, T2 after dash Tx. Based on the Hund's maximum multiplicity rule, always singlet state having more energy compared to the triplet state. But there is no ground state of the T0. T0 is not possible because all the molecules in the ground state level which is existing only the S0 level, because which is having which one? Pairing of the electron in the ground state. When it's pairing of the electrons which is possible in only in the ground state, pairing of electrons is there. So that's what always S0 is possible, T0 is not possible. So that's what S0 is possible. S0 is possible here in this case. So this it may be there, S0 like this. Order is also there according to the Hund's arrangement, that is singlet state having more energy than the triplet state. Leave it that. So now here in this case, why this concept will be explained, singlet and multiplicity, based on the multiplicity, also the electronic transitions which are possible. This one is also one of the rule, will further governs the electronic transitions. That means which one is allowed, which one is forbidden. Forbidden is also, forbidden means here it is having low intense band which is possible. Because in UV visual spectroscopy, instead of sharp peaks, we have to consider as the band. Right? I already explained in the last class. We have to consider the bands. Right? Not consider as the peaks. Sharp peaks which is not possible. Only bands will be possible because vibrational, rotational and electronic levels will be merged in the UV visible spectroscope I mentioned in the last class. So now here in this case, the selection rules which is selection rules For UV visible spectroscopy or electronic spectroscopy, which one is the selection rule? See, listen. First one, based on the symmetry criteria, I mentioned this based on the symmetry criteria, the selection rule. Which one is having the selection rule? Just before I can explain, based on the center of inversion, or inversion center. So if it is having gered and ungered, I can explain. We know that sigma orbitals is gered and sigma star is ungered. Pi is which one? Ungered. Pi star which one will be gered based on the center of inversions. Just before I can explain. Now based on the symmetry criteria, the electronic transitions are allowed. Only in which one case? The electronic transitions are allowed in which one case? When it is the molecular orbitals, whatever these molecular orbitals having same symmetry, if it is there, which is not allowed. Molecular orbitals having different symmetry, which is there, different symmetry. So that means if it is gered to ungered and ungered to gered, gered to ungered and ungered to gered. So which is having different symmetry, gered, ungered to gered. So these electronic transitions are only should be allowed transitions, Even though bonding to antibonding is possible, I can explain non-bonding to antibonding, but the electronic transitions which can be allowed based on the symmetry rule, gered to ungered and ungered to gered. This one is one of the case. And if it is molecular orbitals having the same symmetry is there, gered to gered and ungered to ungered, if it is there, which is not allowed. Transition. This is not possible transition. This one is allowed transition according to the symmetry criteria. That means suppose sigma star, pi star, like it may be there. Sigma to sigma star is possible or not? Possible. Gered to ungered. Sigma star to pi is possible. Sigma star to pi is possible or not? Ungered to ungered is not possible. General one case, suppose. But sigma star to sigma is possible. Sigma star to sigma is not possible because anti-bonding to bonding is not possible. I mentioned that bonding to anti-bonding is only possible. Even though you can check bonding to anti-bonding case only. Even though bonding to anti-bonding case, that means sigma is bonding, sigma star is anti-bonding. Bonding to anti-bonding is possible, but anti-bonding to bonding is not possible. Even though it is, which is having symmetry is allowed, but the criteria is, first I can mention the criteria is bonding to anti-bonding and non-bonding to anti-bonding only, right? Next one, because without having electron, anti-bonding to non-bonding, anti-bonding to bonding, how the electron transition is not possible, because anti-bonding is having no electron. There is no electron, there is no chance to the electronic transition, right? So this is one of the symmetry criteria. Another one which is based on the multiplicity criteria, if it is same multiplicity, if it is there, if it is having retention of spin during the electronic transitions, during electronic transition, if retention of spin is there, if it is retention of spin, which is allowed transition, retention of spin. And if inversion of spin is there, if inversion of spin during electronic transition, if inversion of spin is there, that it may be considered as forbidden transition with low intensity, with less intensity is there. Forbidden transitions are not allowed transitions. Forbidden are not allowed sometimes. That means before it may be ground state is what? S naught. If retention of spin takes place, same spin it may be there. Suppose which one it may be there? S1 if it is first excited, second excited S2, like that it may be there. And if it is inversion of spin takes place, which one levels which will be generated? T1, just before we have seen T1, T2, like that. So now the electronic transition from the S0 to S1, which is possible or not? With retention of spin, if it is there, S1 will be generated. Retention of spin only, S1 will be generated. Retention of spin. This is which one? Inversion of spin. The earlier one we have seen this, S1, T1. With retention of spin, that it will be allowed transition. This it may be which one? Allowed transition. Allowed transition. And with inversion of the spin takes place, S0 to T1, this one, which is going to be forbidden transition. Based on this. Right? So S0 to T1, which is going to be not there, forbidden. Forbidden transition. So that means having same spin multiplicity which is allowed. According to the multiplicities, having what we can say that same spin multiplicity, same multiplicity, same multiplicity, singlet to singlet, triplet to triplet, like that. Singlet to singlet and triplet to triplet only, which will be allowed transitions, right? Singlet to triplet and triplet to singlet, which is not going to be allowed transition. Electronic transitions are not allowed from multiplicity change. If it is there, it is not allowed. Same multiplicity is having there, that it may be follows allowed transition, right? So this one will be allowed, but singlet to triplet, what will happen? Which is not going to be allowed. Singlet to triplet, which is not going to be allowed transition. This is one of the selection rule. One rule is the symmetry, another one is it may be the multiplicity criteria. And in addition to that, another one more point is also there. In addition to that, based on the angular momentum, another one selection rule based on the angular momentum. What is that selection rule? I can explain. Based on the angular momentum. Based on that angular momentum, listen. If it is change in angular momentum, change in angular momentum of electrons, delta L, change in angular momentum of electrons, delta L, if it is 0 or plus or minus 1, 0 or plus or minus 1. If it is there, that electronic transitions will be allowed electronic transitions. That electronic transitions will be allowed electronic transitions. Allowed electronic transitions. And another one in the case of the, compared to the case of the non-bonding case, what will happen in the case of the non-bonding electrons case? So if it is the molecular orbitals having the same symmetry, even the molecular orbitals case having the same symmetry, or it may be the parallel arrangement which will be there. The molecular orbitals having parallel arrangement, in plane arrangement, parallel arrangement or in plane overlapping takes place. In plane or good overlapping takes place. Parallel arrangement it may be takes place. So n orbitals and pi star orbitals having the same symmetry molecular orbitals, n and pi star, like that. It is overlapping takes place. N and pi star orbitals. Or it may be pi star is like this, suppose n it may be there, due to some overlapping takes place, it may be due to the bendings and twisting, some of the changing it may be takes place, that it may be slightly overlapping takes place, right? So if it is parallel arrangement it may be there, or in plane arrangement it may be takes place, n and suppose pi star having same parallel arrangement it may be there. So if it is same arrangement it may be there, good overlapping takes place, then electronic transitions will be allowed. Electronic transitions will be allowed. So here in this case forbidden means which cannot be possible also, even though which is not possible, but here in this case which is possible. If this is allowed, even forbidden is the less probable transition is there. Allowed means here it is having more probable transitions. More probable electronic transitions. And which is anti-parallel, which is there, or perpendicular arrangement is there. The molecular orbitals having perpendicular arrangement, it may be there. N and sigma star. N and sigma star combination. So when n orbitals having like this, sigma star orbital having like this, it may be there. Sigma star is having like this and n is there. So due to this sigma star, right, so the overlapping which is not possible, perpendicular arrangements are there, right? I'm not going to detail discussion, but perpendicular arrangement which is there. So which is perpendicular arrangement is there due to the n2 sigma star, this it may be forbidden. Forbidden means it is also possible here in this purpose, but which is less probable transition. This is more probable transition, this is less probable transition. Less probable transition means less intense transition. Intense of the band is also very less. This is more intense band, less intense band. More intense, more height it may be there, or peak width it may be, peak height it may be more, band width, band height is also more. In the case of the UV visible spectroscopy, that it may be considered as in the terms of epsilon maximum. I mentioned that in the earlier one in previous classes. Epsilon maximum you have to consider, that it may be considered for the intensity point of view. Intensity can be measured by the epsilon maximum. And position of the band which can be measured by the lambda maximum. Position can be measured by the lambda maximum. If it is 200 to 250 nanometers which is there, out of which one is considered as the band position. I mentioned that where that maximum absorption takes place, that position wavelength which is considered as the lambda maximum, that it may be the band position. So instead of the sharp peaks, merging of the so many levels which is there. So due to the merging of the levels, so this band instead of this sharp peak, this will be appear, band will be appear in the UV visible spectroscopy. Vibration levels, rotational levels, as well as electronic levels, which is the merging takes place. I mentioned in the previous class. So due to that, instead of sharp, broad bands will be there in UV visible spectroscopy. In IR spectroscopy or vibration spectroscopy, somewhat compared to this, somewhat broad it may be there. Not fully broad, somewhat like this. So in microwave spectroscopy, sharp peaks which will be obtained because only rotational levels are involved. In IR case, rotational vibration levels also involved. Here in this case, rotational, vibrational, electronic levels also merging takes place. So that's what the peaks will be different. Will be IR like this, microwave like this, and UV visible or electronic spectroscopy like this. So this is which one? Lambda maximum. Now the intensity. This how much intensity, how much height it may be there, that it may be measured by the which one? Epsilon maximum. Epsilon maximum is measured, that is the intensity of the band. That measure the intensity of the band. Position and intensity. Position is which one? Lambda maximum. And intensity is epsilon maximum. So that it may be there. This is one of the criteria according to the molecular orbitals. According to the molecular orbitals, that it may be the selection rule if it is there. Further it may be another one. If it is symmetric energy criteria is also there some cases. So suppose you have to consider the 200 to 800 nanometers range of energy is there. 200 to general UV visible range is how much? 200 to 800 nanometers range it may be there. If electronic transition should be possible, suppose that energy level 200 to 200, 800 if it is possible, that energy is available 200 to 800, that transition only possible, general UV visible case. Suppose that energy, whatever the electronic transition takes place, the energy which is not available for 200 to 800, suppose based on the energy criteria, that transition is also not possible, even though, right? If it is energy is available, that is possible on that particular side range. If it is that energy is not available. Next another one is the possibility of electronic transitions. So suppose the molecules having only sigma electrons are there. Only sigma electrons are there. What will be happen? Only sigma electrons are there. like CH3, if it is there. Sigma electrons are only there, right? So in this molecule, C2H6 like that, right? So in this molecule, what will happen? Only sigma electrons are there. Sigma electrons means which one is there? Sigma bonding molecular orbitals are there. Sigma bonding is only there. So sigma bonding means sigma bonding molecular orbital, sigma star anti-bonding molecular orbitals. Sigma star anti-bonding molecular orbitals. There is no pi bonding, there is no lone pair of electrons. So that's what, there is no non-bonding, there is no pi bonding. Only sigma and sigma star will be there. So if it is in this, so compared to the energy of the sigma and sigma star, which one is having more energy? Sigma star is having more energy because anti-bonding molecular orbital. Sigma is having bonding low energy molecular orbitals, right? So this is bonding, this is anti-bonding molecular orbital. So sigma is bonding means electrons which will be filled already, so that it may be considered as also HOMO level. This is also considered as an LUMO level like that. Bonding and anti-bonding which will be there. So electronic transition is possible from bonding to anti-bonding is there or not? Bonding to anti-bonding. So here it is, the possibility is only one possibility. By the, how this electronic transition is possible? By the absorption of the, which one? UV visible range of radiation. Some energy will be needed because when electron jumps from one level to another level, some energy will be compulsory. So whatever that, this energy will be which one level energy? UV visible range of radiation if it is absorption takes place, and taking that energy, an electron may jumps from sigma to sigma star level, so that it may be going to be jumping of the electron or promotion or shifting of the electron from sigma to sigma star level. So that's what electronic transition is possible. So in most of the case, when it is having sigma electrons is there, the required radiation energy will be nearly, here it is 135 nanometer radiation range of energy will be required. So this it may be considered as for UV or vacuum UV radiation, for our vacuum UV range of radiation, which is not available in the 200 to 800, which is going to be 10 to 200 range, which is going to be available, which is high, very high energy radiation, very high energy radiation which is required. Lower wavelength, high energy is there. So 135 nanometer wavelength of the radiation which is required, that position of the band which is possible. At which one? 135 nanometer range, position of the band which is possible, that is going to be CH3. Now here it is sigma to sigma star transition, I can mention that, bonding to anti-bonding. So sigma orbitals are which one? J-red. Sigma star is un-J-red. J-red to un-J-red electron transition is possible or not? Possible. Right? So if it is molecule having sigma electrons are there, whatever the molecule you can take, only sigma electrons are there. Which transitions are possible? Sigma to sigma star. Sigma to sigma star. Next, the molecules having both sigma and pi electrons. That means both sigma and pi electrons. Both sigma and pi electrons. So what will be happen? See, listen, for example, CH2 double bond CH2. CH2 double bond CH2. What will be happen here in this case? Sigma bonds are there and pi bond is there. Sigma as well as pi bond is also there. So bonding is there automatically, anti-bonding is also possible. Anti-bonding or empty band which is there, empty bonding. So that means sigma, based on the energy criteria, sigma orbitals which is more stable, sigma electrons which is more stable, like this considered as low energetic, and compared to the pi bond, partial overlapping takes place. This is a direct overlapping takes place. Again, another one it may be the pi star, another one which is having the sigma star. Sigma, pi star, sigma star, based on that energies. Right? Whatever that the high energy is there, unstable. Low energy is there compared to that stable. So these two are which one? Bonding. These two are which one? Anti-bonding molecular orbitals. Bonding molecular orbitals means having which one? Pairing of the electrons which is there. Right? Now here in this case, how many possibilities which are there? Listen. Bonding to anti-bonding, general our criteria. One is it may be sigma to sigma star. Second, sigma to pi star. I just mentioned generalized case. Another one which is going to be pi to sigma star. Another one chance it may be the pi to pi star. Generalized case, bonding to antibonding case. Out of which one is allowed, which one is allowed, which one is forbidden, or which one is not allowed? See, listen, sigma to sigma star, sigma is what? Gered. Sigma star is what? Ungered. So ungered to gered transition is possible or not based on symmetry criteria, which is having possible. And sigma is what? Gered. Pi star is what? Gered. Gered to gered, which is not possible. Gered to gered having same symmetry, which is not possible. So that's what sigma to pi star, the transition which is not possible. Right? Next, pi to sigma star. Pi is what? Ungered. Sigma star is what? Ungered. So this is also not possible. So that means pi to sigma star, this transition is also not possible. Next, pi is what? Ungered. Pi star is gered. Different symmetry which is there having possible. So out of which, how many transitions are possible? Sigma to sigma star is possible. Another one is which one? Pi to pi star is possible. Remaining one which is not possible. Sigma to sigma star and pi to pi star which is going to be possible. Only two transitions will be possible. Right? So this is the molecules having both sigma and pi electrons are there. Which one transitions are possible? Sigma to sigma star as well as pi to pi star. Remaining all transitions will be ignored. Right? So based on this criteria. Right? Another one which is having molecule having, in addition to that, sigma pi electrons, if it is having lone pair of electrons also there. If it is having lone pair of electrons, what will be happen? If it is having lone pair. Here we have seen lone pair of electrons also there, what will be happen? Molecules having sigma, pi and non-bonding or lone pair of electrons. Lone pairs or non-bonding electrons. Lone pairs or non-bonding, if it is there, what will be happen? Lone pair, sir, which is not participated in the bonding, that is lone pair. So molecule having sigma, pi and lone pair of electrons is there. So how can you say that? Listen. For example, I can mention carbonyl is an best example, or acetone molecule, or simply I can take acetone molecule. Acetone, right? Here how many lone pairs are there? Two lone pairs are there here in this case, in the carbonyl chromophore of the acetone, particularly in acetone molecule. These are acetone molecules, CH3 and CH3C11O. Right? Here in this case, which one is there? Sigma bonds are there, pi bonds are there, and which one is there? Lone pair of electrons are there. Right? Lone pair of electrons means non-bonding molecular orbitals. So here it is, sigma, pi and non-bonding is there. Listen, one is which one? Sigma. Alright, sigma is there automatically. Which one is there? Sigma star, anti-bonding molecular orbital. Next, pi molecular is there. Pi bonding is there or not? Pi is there. Again is going to be pi star molecular orbital. Next, another one level which is there, non-bonding molecular orbitals also there. Non-bonding, that it may be considered as N. Because lone pair electrons is there, only non-bonding levels are there. See here, two lone pair electrons are there here in this case. One lone pair electron which is participated in the sp hybridized with the sigma bond formation takes place. With the C and O, sigma bond formation takes place. One sigma bond formation takes place. This sp is having the this sp hybridized orbital which is participated in the sp hybridized, and which is the px, which is located to the px, right, in oxygen. So even is oxygen which is there like this, 1s 2s2 2p 4 which is there, 2s2 1s2 2s2 2p 4 which is there. So this is the 2p4. So here it is px, suppose you may imagine py, suppose pz, you may imagine this is what 2s, right. Now this 1s and this 1p which is going to be sp hybridization. In this case oxygen is going to be sp and this carbon is going to be sp2 hybridization. sp and sp2 and sp hybridization takes place. I am not going to be detailed discussion here in this particular point of view. The bonding which is carbonyl I cannot going to discussion, though it is having sp and this is sp2 hybridization takes place, right, which is having 1s2 2s2 2p2 and one of the electron which is jumping from the 2s2 to 2pz. So that's what 2s1 2p3 is there, 4 it may be there, right. So one of the electron which is participated bonding with the oxygen atom of this one pz, right. So py and sp which is there, sp, this one lone pair is there, that it may be the sp lone pair like here in this case, sp bonded lone pair, right. One electron is participated in the bonding with these two, right. Another one px is here in this case, and pz will be participated in the pi bond formation. One sigma bond formation case this one, and pi bond formation case pz, and whatever the lone pairs are there, one is sp lone pair, another one is the px lone pair which is there, right. So in the oxygen case this is, right. Now here in this case one is sp lone pair, another one is px lone pair. According to the, if you can see the molecular orbital energy level diagram of the CO, one side is C, another one side is O. Based on that, this sp, here it is sp hybridized orbital which is whatever that is there, that is having low energetic. Sp hybridized orbital is having low energetic because he is having participated in the bonding. Sp hybridization is having low energetic, somewhat considered to the stabilized, right, which is not participated in the bonding, which is not participated in the bonding. So which is not participated in the bonding means which is not participated in the electronic transitions, right. So which is having stabilizer which cannot involve in the electron transition. Which one is involves? px, the lone pair which is having involves in the carbonyl. Which one lone pair? That is non-bonding lone pair which is having particularly px, that it may be 2px lone pair, right. If it is particular, suppose if it is specially asked, suppose question in that oxygen, which one lone pair is participating? 2px lone pair only. sp hybridized lone pair which is going to be stabilized, having low energetic, which is not involved in the electronic transitions. The non-bonding electron which is having involves 2px only, right. So it may be discussion also takes place, but I am not going to be detailed discussion of the carbonyl molecular orbital energy diagram. So now here it is, sigma bonding is filled and this one is filled, and even though non-bonding is also filled, we know that px is empty, right. Non-bonding is also filled, and these two are anti-bonding. These two are anti-bonding which is empty bonds, right, which is not having electron. Based on that, which one will be possible? Based on that, so which electronic transitions are possible here in this case, right. Which one is possible? See, listen. The possibilities. One possibility is what? Generalized case. Bonding to anti-bonding is possible. Our conclusion, non-bonding to anti-bonding is possible. First one, this one, sigma to sigma star. Suppose sigma to pi star. And next, pi to sigma star. Pi to pi star. Bonding to anti-bonding. Next, non-bonding to anti-bonding. N2 sigma star, N2 pi star. So total, if it is, how many is possible generalized case? One is sigma to sigma star. Another one is which one? Sigma to pi star. Another one which is pi to sigma star. Another one which is having pi to pi star. Another one which is having N to sigma star. Another one, last one, which is having N to pi star. Right? Total 6 generalized transitions, which is 6. Out of 6, which one is allowed, which one is forbidden? You know that sigma is what? Gyret. This is ungyret. This is possible. And sigma to pi star. This is gyret. This is gyret, which is not possible. Pi to sigma star, this is ungyret, this is ungyret, which is not possible. Pi to pi star, this is gyret, this is ungyret, this is gyret, which is possible. And now in the case of the N2 sigma star, what will happen? N2 pi star. The N and sigma star is having perpendicular arrangement is there. Perpendicular arrangement is there. N orbitals having sigma star orbitals. So if it is due to that, some of the twistings and some of the in-plane arrangement, if it is rotations takes place, that it may be going to be overlapping takes place, but it may be partial overlapping takes place or poor overlapping takes place. So that's what this it may be forbidden. We may consider this it may be the forbidden because pure overlapping takes place. Both are in the parallel arrangement is there. And N and pi star orbitals having good overlapping, it may be there, right? So both are having parallel arrangement is there. Here perpendicular, here it is parallel arrangement is there. So the N and pi star orbitals, if it is parallel arrangement is there, good overlapping takes place. So this it may be allowed transition. So now how many electron and this 200 to 800, whatever this sigma to sigma star, listen, sigma to sigma star, if it is transition is possible, the required energy is more compared to this one because sigma to sigma star having large energy gap is there. If electron jumps from this sigma to sigma star level, more energy is required. More energy is required. When more energy is required for the sigma to sigma star, that is available at which one case? Very lower wavelength cases. Lower wavelength cases because lambda is inversely proportional to the energy. More energy is there, lower wavelength, or less energy is required, higher wavelength. So sigma to sigma star, which is large energy gap is there. Suppose this energy, if it is available in the very lower wavelength case, nearly that it may be going to be far UV or vacuum UV visible ranges. Far or vacuum UV visible ranges. So that's what far or vacuum UV visible ranges only that it may be possible. So that's what naturally or generally which is not available in the 200 to 800 nanometers range. If it is not available in the general UV visible range of the 200 to 800, this is also not considered. Generalized, general UV visible range case, or otherwise this is possible. If it is far UV range, which is possible, 165 nanometers range nearly it is possible, but it is less than 200 nanometer, right? So general UV visible range is 200 to 800 nanometers. So that's what, based on energy criteria only, we can eliminate or we can possible, we can say that, right? So, but here it is generally which one is considered? Sigma to sigma star is considered. Another one which one is considered? Pi to pi star is considered. Sigma to sigma star, pi to pi star. Another one which one is considered? N to pi star. N to pi star. Based on energy, this is considered, right? And in general, the acetone molecule case, in general, in acetone case, we can use two types of these two transitions. One band which is possible at 188 nanometer. This band, it may be the pi to pi star band. Lambda maximum of pi to pi star. Lambda maximum of pi to pi star band, which is possible at 188 nanometer. In the case of the which one? Acetone molecule, particularly acetone molecule, right? Another one band which is possible with low intensity compared to this pi to pi star having low intensity. N to pi star is, even though which is perpendicular arrangement, is even though it is allowed, but compared to the pi to pi star, the intensity will be less. Pi to pi star is high probable transition, more intense transition. This is less intense transition. which one? N to pi star. So the lambda maximum of N to pi star, in this case, which one here in this case? 279 nanometers. 279 nanometers. So most probably two transitions which is possible. Based on the energy also, sigma to sigma star is also possible. So more particularly in the case of the acetone, this band which is considered as the K band, this band which is considered as in the acetone molecule K band, and this band which is also considered as R band, N2 pi star band which is considered as R band. So K and R, it may be the Latin words, sorry, German words. K means conjugate. And this is also radiclifter, something it may be there, right? So conjugate and radicliftering. So this is both are, it may be the German words. R and K band also sometimes it may be considered. R band and K band which is in the acetone molecule. So you have an idea about the molecule having lone pair electrons. Is there what will happen? Molecular having sigma electrons, molecular having sigma and pi electrons, molecular having sigma, pi and lone pair electrons. Another one choice is also there. Molecules having sigma and n electrons are there only. Suppose methanol is there. Here it is having which one is there? Sigma electrons are there only and n electrons are there. So when sigma electrons are there, which one is there? Sigma as well as sigma star. And non-bonding is there? N. So non-bonding is filled, bonding is filled, anti-bonding is empty. Which transitions are possible here in this case? One is sigma to sigma star. Another one is also N2 pi sigma star is also possible, but which is less probable transition. Less probable transition. The intensity less probable means forbidden means the intensity is very less. Height of the peak is very less. Less probable transition N to sigma star. Most probable transition is sigma to sigma star. Even the N to sigma star, but is less probable transition. Very less. Here in this case, we can ignore that transition is also. We can ignore that also. N2 pi star, pi to pi star, we can consider based on the energy sigma to sigma star transition also we can consider. So this is having the electronic transitions which is possible in the molecules. Electronic transitions possible in the molecules. Right?